Yeah, good morning, good afternoon. Welcome for joining. In my part of presentation, I would like to talk about regulations, guidelines, trends for PFAS analysis from European perspective. And of course, I will talk also on science solutions. Short outline, my presentation will be majorly on two parts. PFAS in food and PFAS in water. As we all know, the guidelines and regulations are quite different for food or water, and also because the institution and government body to give out the regulation guideline are quite different for these two aspects. Yeah, first, PFAS in food. Yeah, in August 2022, EU Commission published a document, what you could see here, screenshots, EU 2022-1431. This is a recommendation on monitoring PFAS in food. In this document, you could find that EU determined that 4 top PFAS compounds has to be tested. These 4 top PFAS compounds are PFOA, PFOS, PFNA, and PFHXS. And also in this document, you could find for different matrices what is the MRL maximum residue limit for these 4 top PFAS compounds. So here is just the screenshots. You could find what is actually suggested. MRL for milk, for example, and for fish oil, for example, here. And you could find all the numbers there. So same year, 2022, European Commission published in December another document. Document number is 2388. What you could see actually from screenshots, the title here already, the difference between this one and August one. This one is not suggestion anymore, it's enforced regulation. So that means any number MRL you find in this document is enforced for your food testing. So any products on the market, if the testing level is above the level allowed in document, that is a positive sample is not allowed to sell on the market. So there are also few other difference here. So this document is more focused on food from animal origins. That means if you are looking for levels for vegetables, for example, you still need to check with August recommendation document. Another difference is in this document, EU Commission also put another value here is called sum of those 4 top PFAS compounds. The 4 top PFAS compounds are not changed, still the same, but you need also look to the sum of these 4 compounds, the quantitative results, the amount in these 4 of these 4 compounds in total, to sum of them together. So if each of them are below the MRM, but some of them is above allowed of total, this sample are still positive. Yeah, together with these 2 regulations, a European Reference Laboratory, EURL, also published a guideline for PFAS testing according to these 2 European regulations. So the name of document is EU POPs. In this document, actually, you could find many requirements, for example, how you should do your method validation. Another point is also the requirement for the PFAS testing scope is extended here. It's not only for these top 4 PFAS compounds, you need to test at least 32. The scope in the guideline is for 32 PFAS compounds in total. In this guideline, one of very important points is how you could define limit of quantitation for your samples. So the statement here is very clear. The LOQ must be based on experimental data amount of what you spiked in matrices. That means any kind of calculated LOQ. For example, some people will they measure in very high concentrated sample, look at the signal to noise and back calculate, and what kind of concentration maybe will give you a signal to noise of 10. This is not allowed for PFAS testing in food anymore. And also, of course, one thing I would like to mention is that for all the testing and all your method, according to the SANTA guideline, 2 ions, and also their ratio is required to determine your quantitative results. Yeah, very quick on the guidelines regulations. All the documents you could download from internet from the European Commission Food Safety page. And now I will show you the possible SciEx solutions for the PFAS testing in food. Yeah, when we talk about LC-MS method approach for PFAS testing, I think 3 steps here are quite essential for consideration. And sample preparation, LC method, and also MS method. The solutions I will show you today is all on SciEx 75 plus instrument. Since this instrument is a very sensitive, our high-end instrument. So regarding the sample preparation, what we want to use is so-called dilute and shoot, and with some optional for cleanup, but we do not need to do SPE pre-concentration. And from SciEx on 75 plus, we do have a MRM database for all many PFAS compounds. This is definitely more than even the guideline required 32 compounds. We could get the instrument condition and transitions from the database. And also we are using state-of-art LC method. For the method details, we publish that in 2 tech notes. Those 2 you could actually download from our homepage, sciex.com. And in the details are all in these tech notes, for example, how the sample is prepared and what is the LC condition. And of course, we did not list all the MIM transitions in tech notes itself, but you could get information from us. So the first one is a tech note we did together with FERA, and actually we run a ring trial samples from FERA. And second tech note is based on a method developed by Nestle and a method validated by Nestle too. And we put with Nestle together on the tech notes to highlight what is important and what is the important steps to be able to get the results. Actually, they validated on 75 triple quadruple instrument. Yeah, like I mentioned before, I do not have time today to go into each method in detail on the LC, on MIM transitions. You could find all of them from our tech notes. I just want to point out some very important key features, what you should reach or you should get from your method. The first thing is that because of many PFAS compounds, you do have isomers, linear and branched. And because of some guideline required unratio conformation, and your standard maybe only obtain one part of these isomers. So even there do not have very clear statement in the guideline, you do need a method that be able to separate linear and branched isomers. This is what we provide you the method in first tech notes, where you could see for both PFOS and PFHX. Those are 2 of the 4 top compounds, and the isomer are clear separated. Yeah, if you remember, the EU POPs guideline required that all the LQ determination must be experiment data. So this is what we did in the first tech notes. We injected standards with 2 microliter injection. And what you could see here is the LQ, what we could determine what is the signal to noise. And all the LQ is also determined by 2 transitions. For example, what you could see here for the PFBA and PFPEA, the LQ could be much lower if we only consider one transition, but not the case. The LQ we give out here is based on 2 transitions and the correct unratio. Yeah, here are XICs for the top 4 PFAS compounds in EU 2388 regulations at their AOQ level, what we give out. What you could see here, size-wise, show very nicely 2 transitions, and the line here indicated the unratio and unratio tolerance. Of course, the tech notes is in collaboration with FERA, and we run their rain trial samples in matrices. And in this table, we just show you some example PFAS compounds. In the middle here, what you could see is the quantitative results we reported back to FERA, and on the right side is from FERA published the average results, what they got from all different testing labs. What you could see here, that is just an example in pork level as the matrices. What you could see, the results, what we reported is very close to the FERA reported the average results, and that means the results is very close to that what it should be. Yeah, those XICs of one example PFOA compound from pork liver as matrices. Like I mentioned before, all the samples, matrices and spiked in matrices and our standard we got from FERA as their rain trial testing samples. What you could see here, actually, we use a standard solvent, standard insolvent as a calibration curve. Because of sensitivity of the 75, we could inject quite small amount, in this case, just 2 microliter. And to quantify the PFOA in matrices, which you could see here, because the results what we reported is quite close to the correct one, we say that the matrix effect in this case is not very high. Recovery is in the range because of the sensitivity of the instrument. Yeah, the rain trial samples sent to us like I mentioned before, are standards, blank extractions, and spiked blank extractions. The results for spiked, the standard spiked in blank extraction, the results reported to FERA, and like I showed you before in the table, the quantitative results are quite close to what it should be. And also I mentioned 75 plus is a quite sensitive instrument. In that case, we also saw some peaks with two transitions and correct ion ratio already in the blank extraction without any spike. So in this case, we also could quantify these three PFAS compounds in blank extraction with the quantitative amount. And but for PFHXS, what we saw is actually a peak for the first transition, but now clear peak for the second transition. Therefore, we say, okay, for PFAS HXX, we did not see any positive results in the blank. Okay, with that, I hope I show you the method, quite a reliable method in our first tech notes to get correct quantitative results with all the requirements and also the sensitivity of 75 to be able to run even without a spike in blank extraction. Okay, so now let's move to the second tech notes. Actually, the method is developed and validated by Nestle using 75 instrument, and like I said, all the sample prep information and what is the validated results you could find on one side is Nestle published a publication, and then another side is also you could find information from our tech notes. Yeah, both in Nestle publication and also in our tech notes, you will see there's a very clear table. There is to say, okay, for these top 4 PFAS compounds, which is regulated in the EU regulation, what is actually in different matrices, what is the value it is required, what is the achieved value from the Nestle validated method. What you could see, they're quite different because, for example, for infant food and young children food, that's actually is not really regulated in 2388. You have to go back to the suggested value in the first document, which I showed you, and you could see the level there is very, very low, the required level. In these slides, I just want to show you actually Nestle validated results, and you could see why this method is reliable and for routine use. On the left side, show you the results for the top 4 PFAS compounds. What you could see when you spiked one-time AOQ in the matrices, if you look at the CV, smaller than 20% of CV, if you look at here are different matrices, but really for 2 matrices is quite difficult one. Not all of these 4 could pass CV below 20%. But if you look at the CV below 25%, which is acceptable for the validation, all those top 4 PFAS compounds could pass in different matrices. And the right side is another part of a validation. The method from Nestle is not running only these 4 top 4 compounds, and also not 32, what is required by PFAS POP guideline, they are run in their methods. They running much more. I think the total is 57 compounds. So if they look at those 57, they spiked in 1 times AOQ and 5 times AOQ. For the validation, what you could see for certain matrices, maybe few compounds will not pass the criteria of the CV. But if you look at the 5 times AOQ, most of compounds will pass. And like I say, this results is much more than guideline regulation required. They are running, I think, 57 compounds in total. Okay, now let's look at the PFAS testing in drinking water. PFAS testing in drinking water actually is regulated before the PFAS in food. In 2020, European Commission published a Drinking Water Directive. In the directive, it's very clear states what is the level for the PFAS which is allowed in drinking water. In this case, there are some difference. It's not regulated top 4 compounds like in food. And for the drinking water, the directive actually divided the PFAS in 2 parts, one short chain up to certain lengths and the long chain. What they say is for the short chain, the total of them added together should be below 100 nanogram per liter. If you find any long chain PFAS here and add them together with a short chain, should not more than 500 nanogram per liter. Yeah, in this table, I just put an example together to see how different is that if you look at regulation for drinking water from region to region and from different organizations. Even like I mentioned, for European Drinking Water Directive, you have 100 nanogram per liter for the short chain PFAS 20, and the total should be 500 nanogram per liter as highest limit if you calculated them together. But even for different member states in the European Union, you also have different level. For example, for Netherlands, they have requirement for those top 4. The level is very low, 4.4 nanogram per liter, 4.4 ppt, and Germany is 20 for this top 4. Even in European Drinking Water Directive, they do not have a requirement for this top 4. And also European Commission said for each member state, they could decide by themselves which guideline, which regulation they will follow. Again, sites do develop the method and solutions for those drinking water testing. It's published also 2 different tech notes. One is on 65 plus, one is on 75. Quick, just HPLC separation. What you could see if you zoom in on the small part here, you could see even the HPLC is not very clear separated, but because of selectivity of mRNA transitions, you could see 2 different compounds here. Just an example, top is quantified ions, and below this one is the internal standard what used for this method. Yeah, in the tech notes, you will find this table that listed the LQ on 65 plus for 3 different kind of water sources. What is the LQ? Like mentioned, it's always with 2 transitions and correct ion ratio. You will also see the sum value of LQs together for both 100 nanogram per liter, this PFAS 20, and also for those PFAS 500 nanogram per liter with longer chain. And what you could see here, the level what you could reach on 65 plus are all below European Drinking Water Directive requirement. Yeah, second tech notes again is a collaboration with one of our customers, a water testing lab in Netherlands, Hatta Water Lab, and in the tech notes you will see this method is validated by them. So you will see two different tables. The first one show you the LQ and signal to noise for different PFAS compounds they included in their method. And the second step, the validated method by spike two different concentrations depends on the LQ, what they determined for different PFAS compounds. They spike them in ground surface water and drinking water. Then they run them by 8 different days and 3 different operators and look at the standard deviation according to Netherlands standard guideline, and then they calculate the detection limit for this validated method. Yeah, those are results for these 3 different kind of water matrices, what they could get, the detection limit for different compounds, all information in the tech notes. Another important thing is because of the sensitivity of 75, actually they could not only go down for their real sample, they could also reduce the concentration of their internal standard to run their sample in routine. So as we know, the PFAS is on one side, the internal standard is quite expensive. On another side, reduce the concentration of internal standard could also minimum the contaminants for your instrument. Now I would like go through very quick on our one of our new tech notes, that's the PFAS in surface water. Again, the tech notes is from a collaboration with our customer in Belgium, VMM. And important thing I want to just show you in this tech notes, you not only see the sensitivity, but also the stability, robustness of the instrument, because the method is also validated by them. So you could find one table show you the LQs for different compounds, which is actually show you the sensitivity. Yeah, that was the sensitivity. Because the method is validated by the customer, they need to run many batches and many samples in different batches through quite long period. In this diagram, you could see the recovery for the different compounds in this time period. So with this, actually, you will see the instrument is not only sensitive, but also very robust for your routine run sample. It's not drinking water, in this case, it's a surface water. Yeah, with this last slide, I really want to show you something on our SAIS OS software. So you can imagine how many samples this customer need to run and how many batches they need to run. And you could also imagine, in this case, data processing and data review is a really very important part for entire method, not only measurement, but data processing and review. And you could also think that is very time consumed. So in this case, with help of our application team and the possibility to use calculated column, we could provide them a final results table with calculated column. This is just an example of screenshots. In this case, you could see actually for which compound and at which kind of concentration they are flagged out. And also you could see actually the reason why this flagged out. So it's much easier and save time for you to have a direct view of your sample. You could find the positive sample, and you also could find something if that is wrong with your calibration curve. You could think if I need to do re-injection. Yeah, now come to my conclusion. First of all, we see that PFAS are heavily regulated in the EU, both for food and water. And of course, now we also know that PFAS is also regulated for other matrices like packaging or like cosmetic, like textile. And we do have also solutions for that. I do not have time today to show that. And the second point is really size, instrument, and workflow. Provide reliable and sensitive and accurate quantitative method. On the sensitivity part, what we could see that for food matrices, we could achieve nanogram per kilogram level, which is required by EU POP guidelines. And for water, validated detection limit is on lower nanogram per liter level. And the last point with one slide, I show you actually SciOS provides powerful tools for method validation. Yeah, with that, I finished my presentation. First of all, I really would like to thank all my colleagues to support us to get the workflow and method done. And of course, also our customers that provide the method and feedback to us so we could work together to solve the problem. And of course, I would like to thank you for your attention.
Hello, everybody, and welcome to my segment of this webinar on PFAS analysis. Hopefully, I'm going to try to keep it informal today, talk about some of the basic things that we encountered during PFAS analysis, talks about some tips and tricks. And to start, I'm going to talk about with some fundamental reasons why PFAS analysis is tricky. And hopefully that will give you all some insight into your own troubleshooting and, kind of working through problems from root cause to finish. So why is PFAS analysis challenging? This figure is from one of our SciEx Tech notes, and it's what we put together as the life cycle of PFAS. And it kind of shows from start to finish, from industrial processing, from firefighting use, from consumer goods. PFAS are kind of everywhere, and not just everywhere in the products that they're meant to be, but from there they enter the environment, they enter humans, they enter animals, and they end up being literally everywhere they're not intended to be. That means from a lab perspective, if you're trying to analyze these chemicals, as most of you know, contamination becomes one of the key issues, usually more than sensitivity or that sort of thing. The first step is contamination, just because of the ubiquity of these compounds. We hear them referred to all the time as forever chemicals, and I would never say never, so I never say forever, but these will be here a long time. Contamination is not going to be something that just kind of goes away for us in the lab. Another thing that makes PFAS challenging is the diverse chemical properties. When we talk about PFAS, a lot of times we generalize. So we say, we're referring to PFOA and PFOS, which are really kind of similar in their environmental fate, similar in their use, but really these compounds can span a huge range of chemical properties. So TFA being the shortest chain, kind of smallest of these perfluorinated acids that we care about a lot. And then PFODA is the octadecanoic, so that's 18 carbons. And then we even get much longer on top of that. What this means is you're trying to analyze a single panel with a huge diverse group of compounds, and it becomes very challenging. TFA being extreme, if not infinitely water soluble, PFODA being an acid, so it's water soluble, but also having that huge fluorine tail that's going to make it very nonpolar and stick to things like sediment. This is really hard for a single HPLC column to, for example, make a good chromatogram for all these compounds. It's hard for a single SPE column to extract all these. So this is one of the huge challenges that face us. And as this analysis tends to go more and more complex, we see more of these side groups, not just acids, but bases, and it's only going to get more challenging from here. Another reason is we see the massive growth of compound lists. So, back 10, 15 years ago, maybe 15, 20 years ago, we really cared about PFOA and PFAS. When 537 and then 537.1 came out, we kind of settled on this list of 18, and that seemed kind of challenging at the time. By now, with 1633, it has 40 compounds, lots of other methods of kind of use this 40 to 50 compounds, and there's much more that you can currently buy standards for. So just the sheer size of these lists, if you're following EPA style or other style QA/QC parameters, you're having to do this times 40. Each compound is its own specific, has to meet all its own specific QC requirements. So it just becomes a massive endeavor to kind of perfect your analysis for each of these compounds at the same time with the same extraction. Yeah, not too easy. And then also here, I put this little figure up to try to just show some perspective. And we just had NBA finals just happened. So this was on my mind. But in 2009, the first health advisories in the US for PFOA and PFAS were at the 200 to 400 nanograms per liter level. So I just converted that to centimeters, and that's like pretty tall basketball player, just for reference here. And over the years, you can see how these levels have come down to the 70 ppt level. So from our basketball player, now we're at the actual basketball size, down to when it went really crazy, down to the 0.004 nanograms per liter. So that's PPQ levels. That would be equivalent to this guy, just a skin cell on this guy. And a lot of debate about whether that was too low, not only too low to be practical in the lab, maybe too low to be relevant, since these compounds are ubiquitous. You would just find them everywhere at that level. In 2024, they updated these to 4 nanogram per liter. So that would be this guy's finger, maybe a good compromise. And the administration right now is possibly reduce this to just PFOA and PFAS. We'll see how that all turns out. But this decreasing level has been a challenge for us in the lab. So not only do we need an instrument that's sensitive enough to reach lower and lower levels, you have to continuously bring your background and contamination to lower and lower levels. So it gets challenging on two fronts there. The other thing that I'm going to talk about today is branched isomers. So these are different structures of PFAS from a very, very helpful paper by the folks at Wellington. These are some of the branched isomers of PFAS that they offer. And if you see, they're showing 11 different structures here. These aren't even the only branched isomers possible. These are just the 1 and 2 carbon branches, right? And what we find with these is not only are they different chromatography, so we end up with these kind of ugly groups of peaks that are unresolved unless you go out to like 15, 20 minutes or longer. But you also get greatly different response factors among the different branches. So these are the same 1 through 11 across the top. So the different branched isomers we showed earlier, where the CF3 is in a different position. And you can see where it's highlighted in red. That is where the responses among these different branched isomers are different from the linear. So by 40% less, or by 40% of the main linear isomer. Or in one case, we can see 0%. So if you're monitoring this 499 to 80, 499 is PFAS, 80 is its sulfonate, so that's that acidic in group. And you have this compound, which is the second isomer branch that we saw earlier. You just won't get a peak. It will not respond. So different labs may have different percentages of these different branches in their standards that they're comparing. And if it just so happens that one lab is using a standard or a PT sample or something that's very rich in some of these kind of oddly great or oddly low responding branches, that can cause lots of confusion and differences among labs. And we see this all the time. I've been involved in some of these PTs where labs come up with really crazy values, and you end up that they were using a different standard than other labs. Not necessarily, it's not wrong. It's just that branch standard has a different kind of fingerprint of these different branches. And when we just integrate the whole thing and assume they all respond the same, that's wrong. They don't respond the same. And you can see up here, if you use the 99, which is, I think, FSO3, you're not safe either, because those two branch also have 0% response. Really, you can see at the top, maybe the safest way is actually to use a parent-to-parent transition. That would be that has, I think, less of a deviation of signal. Yeah. So very interesting paper. You should look that up if you're doing this kind of analysis and you want to be able to explain why your data is wrong or weird. Very good one to know. And so now rules from the EPA, rules from other regulatory agencies usually say if a branched isomer is available in a standard, you have to have it. Used to, that just meant PFAS. So the only one you had to worry about was PFAS. Now, all of these that I've listed are available, mostly from Wellington. So because they're commercially available, you have to use them. So this kind of like unknown of branched fragmentation efficiency and ionization efficiency, instead of just being one or two compounds, it's all of these compounds, because they can technically all have branched in the environment too. Another thing is, if you think about this, these are longer chained PFAS. They come out later in the HPLC chromatogram. There's more time for these branches to separate. When we have things like PFBA and really short PFAS, there's not enough time for them to really separate from their branch. So some different branches can exist there that also might have some of these issues with ionization efficiency and fragmentation efficiency. With all that said, it's just another challenging factor that we have to consider when we're doing PFAS analysis. So what are some things we can do? I've talked about pretty dark and gloomy, and if you're hoping to get into PFAS analysis and you aren't yet, don't let all this scare you away, because if you kind of know all these pitfalls beforehand and you talk to some of your colleagues that are doing this, it can really give you a head start and really help you troubleshoot the issues you might have in your lab. So starting with troubleshooting for contamination, okay, yeah. So we'll start with controlling contamination. Then we'll talk a little bit about optimizing your workflows. There's some flexibility in a lot of different methods, and you can use this flexibility to your advantage or disadvantage, depending on how you use the flexibility. And also, we're going to talk a bit about improving consistency. And that would mean it's not just important how sensitive you are. Once you get your contamination down, it's very important how consistent we can get our analysis, because that's what really is going to matter about how many samples you can do accurately over time. So all of these steps, from your supplies to your SOP to your chromatography, they must be addressed before we even touch the mass spec. So all of this happens. Once these peaks come out, they are sent to the detector. But if all of this isn't good, it doesn't matter how good your mass spectrometry method is. You can only compensate for so much contamination, inconsistent chromatography, that sort of thing. So to start out with contamination, we got some common sources here. We've got the plasticware that you use in the lab. We've got solvents. And then we have the actual lab environment, which can be a bigger contribution than either of these other contributors to PFAS contamination. Um, so um, initially with our plasticware, we partner with Phenomenics, and Phenomenics has gone to a great extent to make their products PFAS free. It's not always perfect. They're always learning. Their PFAS is so hard to actually ever be PFAS free, but we've had very, very good experiences with their things like vials, things like SPE products. Um, Pipette tips, I'll only say beware of coated pipette tips, low binding pipette tips. A lot of those are actually coated with fluorinated compounds themselves, so those can be a problem. Um, with solvents, can be kind of a weird one to think about. Um, we all kind of default to saying use LCMS grade, use LCMS grade, buy the most expensive solvent you have, and that is it's good advice to start with. But what we find, especially with water in the lab, is the LCMS grade water is not always as clean as what you can get through a good kind of well-maintained reverse osmosis system in your lab. So that RO water, since it's created there, it's gone through the filters immediately. It's not been stored. It's not been transferred. It's not seen any contamination after production. Sometimes that's actually cleaner. And you kind of wish you could have a in-lab way to distill your methanol or something like that. But using that lab water or just finding a certain brand or vendor that works for you in your region, extremely important. And then I will say, not only that, it's having multiple types of solvents that you know are good. So once you find that LCMS grade methanol that you like, don't stop there. Try to find another one of another vendor, because you never know when that vendor or that you're going to get a bad lot. So it's always good to have different options. And then controlling contamination in the lab. This is really important because PFAS can live in the dust. It can be floating around in aerosols in the air. You may be stirring up a lot of contamination just during your analysis and during your moving around. So keeping good lab hygiene, keeping your benches clean, keeping the floors clean, keeping everything tidy, having designated areas for PFAS, extremely important for controlling contamination. And then I always tell people this, and I often am guilty of not doing this, but once you are successful, congratulations, yay, you've got that first blank that shows no PFAS background or very minimal PFAS background. Take everything you did and don't just write it down, but take some of those vials, take some of that solvent, take your pipette tips, anything that touched your samples, put it in a box and label that as tested clean for PFAS. Because what's going to happen later is you're going to somewhere down the road have peaks pop up out of nowhere, and you're going to have to go through the whole thing again of saying, is it my solvents? Is it my vials? And having known clean references is just extremely valuable. So I call it your PFAS free time capsule. Lock it away, keep it, things like your internal standard stock mix, just keep a little bit of everything, and you'll really, really thank yourself later. So shifting gears a bit to consistency. Here I have a chromatogram, actually 5 different chromatograms, and this is some real data showing retention time shifting. Retention time shifting is kind of a minor thing in some cases, and in other cases it can be big, it can be kind of annoying, but really it does cause issues with consistency in your mass spec analysis. So if these peaks are eluting a little later, a little earlier, they could be eluting at a slightly different organic content, and many times that can affect the ionization pretty significantly. So if you're having trouble with mass spec reproducibility, you need to first check your retention time reproducibility, because in a lot of cases, the mass spec is just ionizing what it sees coming out of the LC. And if you are consistently changing your retention time over the course of the run, and you see your MS signal, not just the retention time, but the actual signal changing too, this could be a root cause. So that kind of slight or minor retention time shift over, in this case, was 48 hours, was causing inconsistency and causing failures in the quality control samples. The root cause we found of this was the lab was using 95% acetonitrile, which is okay, 20 millimolar ammonium acetate in water, which is also okay. But what we see a lot of times is with late eluting compounds, having this, having no salts in the organic means that an ionic strength is just decreasing over your run, and it's making it less reproducible because the amount of that salt is very minimal. It's something like 80 or 90% B. Instead of having 20 millimolar total, we're having 2 millimolar or 1 millimolar. So there's not enough of those salts to kind of pair with your ions and keep them eluting the same throughout the run at maybe a slightly different temperature or other slightly different conditions. So typically what we see, and with this case, suggested that we change to add the ammonium acetate both in the water and in the acetonitrile. And always know with acetonitrile that you have to have a certain percentage of water in there to add any salts. 95% or 90% acetonitrile with 5% water is usually enough. But doing this minimize that retention time shifting, and it keeps the mass spec signal much more consistent. Oh yeah, I said that down here. I think this is always key. It's one of the first things I recommend for troubleshooting either retention time drift or signal drift is let's keep the ionic strength consistent through the whole run. Let's not, unless you're specifically trying to alter the ionic strength, there's no reason to have it different in your A and B solvents. Okay, so not just consistent retention time here, but another thing we need to focus on is the separation itself. And a lot of times in published methods, we will see something like a 20 or 25 or 30-minute run. And a lot of people, especially in a commercial lab, trying to make a good profit, will kind of run screaming from that and minimize their method time as much as they can. And so I do think it's possible and important to kind of have a strategy of running the shortest method possible. You never want to waste time. You never want to waste instrument time or time of your analyst or turnaround time. But sometimes we do have to compromise the speed of our analysis, stretch everything out, use a longer column, use a lower column oven temperature, just so that components in the matrix, components in the background in your lab are well spread out from your peaks that are eluting, and that they're well spread out from each other, because everything will affect ionization to some degree. And the more separation you have is always going to be better. Using a smaller particle size, always good. Making sure your peaks are kind of symmetrically spread out through your run. A lot of times what you'll see is there's a few peaks, and then they all kind of come out in a big plug at the end. That's a recipe for inconsistency. So really want to change your gradient. There's kind of an art to HPLC of getting all these peaks to spread out evenly over time. And some other little tips of 1633 here. We talked about runtime, but having your auto sampler at room temperature can be very important, especially when you have long chain PFAS in your samples. Storing your standards at room temperature when allowed by your methods is also very important. This just keeps everything soluble and everything consistent in the vial when it's at room temperature. In the refrigerator, PFAS will like to stick to things like the sides of the vials, and then you spend a lot of time bringing things up to room temperature and vortexing, whereas keeping things at RT is typically better if you can. Keeping your auto sampler cool, not so important for these methods. We usually see better consistency when you just turn off the auto sampler cooler. Column equilibration is also very, very important. So before you even run a curve or run your opening CCV, or before you do anything, grab a matrix sample, grab something that you know is kind of going to be one of the dirtiest samples in your batch, and run that thing like 2 to 10 times, as much as you have time for while you're prepping everything else. So not just running blanks before. Running blanks before is fine to get the instrument clean, but why not at the same time run some matrix samples, and that way your mass spec and your column and the whole system is exposed to that matrix and whatever is going to be sticking in there already at the start of your run. So you don't do the common thing where you run a calibration and everything looks good and then your sample's decreasing over time. Go ahead and run those matrix samples first as kind of dummy samples. Then your curve will be more consistent with what the rest of the run is going to see. So in 1633, you have some flexibility. You have flexibility in sample volume specifically. You don't have flexibility in everything, so you have to read these methods very carefully. But this sample volume is not only a way to, this has a few pros and cons, and I'll talk about that in a minute. But the calculations and math you would use, so if your target LOD is 1 nanogram per liter, and the smallest peak on your instrument is maybe 50 nanograms per liter, we know that the final volume of extraction during 6333 has to be 5 mils. You just do this math, and it tells us that our sample volume should be 250 mils. So using your instrument sensitivity to kind of determine what your sample size is very important, because you want the smallest sample volume that allows your analysis to be repeatable. If you have a more sensitive instrument that can go down to maybe 5 nanograms per liter at your desired injection volume, then you could scale down all the way to maybe 25 mils. And scaling down has lots of pros. So everyone would assume it's faster because you're just less volume goes through the SPE faster. Also, there's not just less water in there, there's also less of the particulates that will clog SPE tubes over time. So having a smaller volume is gonna help that a lot. Lower shipping costs, and then I just say happier bench chemists. They all like smaller samples, less time, less things to deal with. But you need a more sensitive instrument. Oh, sorry. And you can actually add less internal standard there. So I said this as cons here. This should actually be in the pros column. You need less internal standard. So you need a more sensitive LC. And then at lower sample volumes, your blanks actually need to be lower. So because you have less concentration factor in your sample, you have less wiggle room in your instrument blanks. And then also less time for bench chemists to listen to their favorite podcasts. Everybody loves listening to something while you're doing a big SPE run. Okay. Also in 1633, you have full control over your cal curve. You have full control over your internal standard concentrations. I often see people starting with a level that's much too high for the sensitivity of their instrument. And so let's see. Yeah. So an ideal concentration is about 5 times the concentration of your native standard. If you go much higher than that, you'll start to saturate your native standard. Much lower than that, and you won't have as good of repeatability. So if you check your PFAS analysis and you're doing 10 times or 50 times your lowest curve point for the concentration of your extracted internal standard and injected internal standard, then you're likely too high, and that could be causing reproducibility issues over time. So I use that 5x rule, 5x your lowest curve point. And the reason is these elute at the exact same time as your compound of interest, and they are actually competing for PFNA, or they're competing for their corresponding native compound for ionization efficiency. Underneath saturation levels, it's not really going to matter. But up to once we hit a certain threshold, you will start to see, and that's what this figure is. If you ever see this kind of quadratic curve shape at a peak area that's not really saturating your MS. So most mass specs can handle, the detector itself can handle much higher levels. It's in the spray, so in the ionization, you're actually getting the internal standards are suppressing your native, and the native is suppressing internal standard at high concentrations. Minimizing that internal standard concentration lets you just extend your dynamic range a little bit more until you'll always hit that threshold. But it lets you extend that dynamic range a little more when you add the correct amount of internal standards. As we all know, in 1633, In a lot of PFAS methods, we have an option between using methanol and acetonitrile as our organic solvent. Methanol is cheaper, a lot of times better availability, easier on your pumps. And acetonitrile has a lot of issues with it being expensive. It's actually kind of hard on your pumps. Buffers, you have to add water, so you can't actually get to as high of a organic concentration. It has a good benefit of faster elution of long chain PFAS. So if you're ever having that problem where your long chains just aren't coming off your column and you're using methanol, consider switching to acetonitrile. But in 1633 specifically, acetonitrile is always going to win because of these torodeoxycholic acids. These are naturally occurring bile acids, especially in fish, but also in human samples and in blood. You really need that separation. And you need the separation. It's a requirement of these methods. If you try to use methanol, a lot of times you have to do a really long run to prevent those bile acids from co-eluting with PFAS. They have the same mass transitions. Without high res, there's really no way to get around that without using acetonitrile. This is very much the easy way. Okay, other tips for optimizing 1633. You can acidify your mobile phase. That will always help early eluters. This can help you inject a little more. So if you're having the problem where PFBA, for example, is coming out in fronting when you're injecting higher volumes, try adding some acetic acid to your A solvent. And depending on your column, especially if you're using a column that has some positive charge, like this Phenomenix PSC18, it's going to improve those early eluters. And then, yeah, using different delay columns is going to help. I have some recommendations for columns and delay columns. And then once you finally get to the mass spec, just be wary of your temperatures, especially for things like HFPO, because if you're cooking too hot, you will destroy those kind of temperature sensitive compounds. And so at SciEx, we have really been trying to push down to lower levels, trying to push down so you can use smaller samples using the 7500 and 7500 plus systems. I'm not going to talk about all this today because you can go out in the internet and search. I put Google search SciEx 7500 PFAS, and you can find a lot of different tech notes where people at SciEx and other organizations have really pushed down to see how low we can go and what you can do with the ultra sensitive instrument platform. And so what's the future of PFAS analysis? I think microplastics is going to be a big thing. So PFAS stick to plastics. We know we have microplastics everywhere. I heard you have like a tablespoon of microplastics in your brain or something disgusting. But all those microplastics also have PFAS attached to them. I say kind of like riding them like a little life raft wherever the microplastics go. And then polymers are fluorinated. They're going to break down. We know very little about fluorinated polymer analysis and what they do. And then kind of my nemesis over the past bit has been ultra short chain PFAS and getting them to properly to have good chromatography. These are very challenging. Talk about contamination. This is, once you get into this analysis, it's the worst you can have. And we do have a tech note on that in case you're interested. And we'll have some other talks on that later. That's a whole different topic. Okay. And that's all I have for today. We can do some Q&A, but thank you for listening. And yeah, reach out on LinkedIn, reach out over email if you have any questions. This is a small community. Everybody kind of knows each other in environmental analytical chemistry, and keep that up. Keep talking on LinkedIn, keep sending messages. Thanks.